and this is radius of the moon. I call this equation 1 divided by r. This is when both mass and radius is given. We measure actual weight of a body. W is equal to, it is very easy to simplify any given problem on this chapter. Hello students, this is SD Sir, again from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. Hope you have watched the previous session of numericals on the chapter Gravitation. Today we will continue further solving numericals from that chapter. The first problem, students. The problem says acceleration due to gravity on moon is 1.7 meter per second square. So the acceleration due to gravity on the surface of the moon is 1.7 meter per second square. And its radius is 0.27 times the radius of the earth. I have to calculate the ratio of the mass of the earth to the mass of the moon. Simple. I have to just calculate the ratio of the mass of the earth to the mass of the moon. Given acceleration due to gravity on Earth's surface is 9.8 meter per second square. So the problem says acceleration due to gravity on moon is 1.7 meter per second square. So small g on the surface of moon is 1.7 meter per second square. And acceleration due to gravity on Earth's surface, GE, is 9.8 meter per second square. And more establishedly, the problem says radius of the moon is 0.27 times the radius of the earth. So the radius of the moon is 0.27 times the radius of the earth. I will have to calculate the ratio of the mass of the earth to the mass of the moon. Now, how do I express and equate all these relations. Now, I'll consider on the surface of the moon. So we know small g is capital G m by r square. What is small g? It is acceleration due to gravity on the surface of the moon. Capital G, this is nothing but gravitational constant. This is mass of the moon, and this is radius of the moon. I call this equation 1. The next one, this is of the earth. So GE, acceleration due to gravity, RE whole square, where m is the mass of the earth, capital R is the radius of the earth. Now, equation 2 divided by equation 1. 2 divided by 1. We have GE by GM. Capital G gets cancelled. ME by mass of the moon into radius of the moon divided by radius of the earth whole square. It gets reciprocal because we are dividing equation 2 by equation 1. Or mass of the earth divided by mass of the moon. That is what we are expected to calculate. So this becomes equal to what? Gravity of earth, gravity on moon, radius of earth, radius of moon whole square. So this is 9.8, 1.7. This is 0.27 whole square. So on simplification, the ratio turns out to be 79. So 79 is to 1 is the answer. The next problem. Here the problem is asking us to calculate the escape velocity of a body from the moon, assuming moon to be a uniform sphere of radius 1.74 into 10 power 6 meter. So we are assuming that moon is a uniform sphere whose radius is 1.74 into 10 power 6 meter, and the mass is 7.36 into 10 power 22 kg. Now, the value of gravitational constant is given. So, we have radius of the moon 1.74 into 10 power 6 meter. I have mass of the moon, which is 7.36 into 10 power 22 kg, and gravitational constant 6.67 into 10 power minus 11 Newton meter square kg minus 2. Now, with this data given, I have been asked to calculate the escape velocity on the surface of the moon. Now, how do I express escape velocity in terms of mass and in terms of radius? We know escape velocity is root 2gm divided by r. So escape velocity is given by the expression root 2gm divided by r. This is when both mass and radius is given. So on substitution, 2 into 6.67 into 10 power minus 11 into, what is the mass? 7.36 into 10 power 22 divided by 1.74 into 10 power 6. So you know the simplification now. First, simplify the numerator, divide it with the denominator, and then take the square root, which is 2.38 into 10 power 3 meter per second. So this is the value of the escape velocity. Next one. A very interesting problem. The problem says, determine the angular velocity. ಯಾವ ರೀತಿ angular velocity represent ಮಾಡ್ತೀವಿ? It is represented by omega. So determine the angular velocity with which Earth would rotate. Earth would rotate on its axis so that a person on the equator would weigh 3/5 of his present weight. A person who is on the equator will weigh how much? 3/5 of his present weight. Radius of the earth is 6,400 kilometer and G is so much. Remember, I am calculating the angular velocity. Under what condition? The person on the equator will weigh 3/5 of his actual weight. Therefore, now we know that true weight of a body, W equals M into G. We measure, no? Actual weight of a body, W is equal to M into G. Now, the apparent weight, I say, W dash is mg dash on the equator. W dash is mdg dash. But how much is W dash according to the problem? It is 3 by 5, the present weight. So this is 3 divided by 5 mg is mg dash. So which means that m and m gets cancelled. G dash is 3 by 5 times G. Now, where is this variation taking place? This variation is taking place at the equator, where G dash is G minus omega square R. While doing the sessions, we have studied variations of acceleration due to gravity. So at the equator, G dash equals G minus omega square R. But what is G dash? This is 3 by 5 G minus G omega square R. 2 by 5 G is omega square R, or omega square is 2G by 5 R. So this is root 2 into 9.8, 5 into 64,000 kilometer. So which turns out to be equal to 7.8 into 10 power 4 radian per second. So the answer is, so this is minus 4, 7.8 into 10 power minus 4 radian per second. The next problem. I have to calculate the mass and density of the earth from the following data. Gravitational constant, we know. Radius of the earth is given. Acceleration due to gravity is known. So the first part of the calculation, it is mass of the earth. Mass of the earth has to be calculated. So we know small g is again capital Gm by r square, from which I have to calculate the mass of the earth. So this is G r square divided by capital G. 9.8 into 6.4 into 10 power 6 whole square. 6.67 into 10 power minus 11. So on simplification, 6 into 10 power 24 kgs. So this is a constant. You should always know this is the mass of the earth. Now calculating its density. Density is represented by rho 3g divided by 4 pi r capital G. Again, I leave the substitution to y'all. So this turns out to be 5.4 into 10 power 3 kg per meter cube. And this is the density of the earth. So again, students, I worked out sufficient revision problems from the gravitation chapter. If you are thorough with these problems, it is very, very easy to simplify any given problem on this chapter. We will meet in the next session. Until then, have a nice time. Thank you.